My name is Jeremy White. I work at INTERA, and I'm going to talk about the generalized adjoint solver that we have developed for MODFLOW 6. Next slide, maybe. There we go. This work was very much a collaborative process with an amazing team, Katie and Joe, three of the smartest people I've ever worked with. This work is very much theirs as much as it is mine. I'm just the one talking to you today. A little bit of logistics. We are recording this webinar. We're going to post it online afterwards, and we're going to send it out to everyone who's registered for the webinar today. Please put any questions you have in the chat. We have Joe and Mohammed actually in the chat today. They're going to try to answer questions in real time. They'll also chime in if I flub things up bad enough. They'll rescue me. And then also all three of us will try to answer other questions at the end. Okay, so for today's talk, I'm going to go through a little bit of history and background about the adjoint method. We'll talk about some mathematics that underpin the adjoint, a little bit of code design implementation, and then we'll wrap up with some examples. So we can't talk about the adjoint without talking about sensitivity analysis. Sensitivity analysis, in my opinion, is a fundamental aspect of applied groundwater modeling. It's what Randy Hunt calls hydrosense developing. So if I change a certain input, what does that do to the outputs of interest, the ones that I care about? Historically, that analysis has focused on simulation of the past, particularly in the calibration context. How does changing this parameter affect the objective function? But I think a much more important form of sensitivity analysis is the sensitivity analysis that's about the prediction, the outputs from a scenario. If I change recharge, how does that change the scenario outputs that people are paying me to make this model for? So two types of sensitivity analysis, both with respect to the past and with respect to the future. Unfortunately, most people don't do sensitivity analysis during model building. They do sensitivity analysis much later in the modeling process. And the reason for that is because sensitivity analysis is computationally expensive. It's a lot of model runs to do a comprehensive sensitivity analysis. So we typically wait till much later in the modeling process, which is unfortunate because sensitivity analysis can teach us important things about the model we are building while we're building it. So most of the time, sensitivity analysis looks like this. We run the model once at our current input values. Then we have this loop where for each input, we change that input sum, run the model, calculate the changes, scale the changes of the outputs by how we change the inputs, and that gives us a sensitivity measure. Oh, wow, I changed this number a little bit, and it really changed the predicted outputs I care about. Or I changed this number a lot, and it had no effect. Those are important learnings about how the model is functioning. But unfortunately, this is very computationally expensive. This is the loop of suffering where you just don't have, especially if your model runs slow, you need a cluster. And even on a cluster, it can take a lot of computational power to do a comprehensive sensitivity analysis. And in this way, with these perturbations, as we call them. This is where we come to the adjoint solver. The adjoint solver is an extremely efficient analytical gradient / sensitivity analysis tool. The theory has been around since the 1970s. It's been revised and developed. It's mature on the theory side. And the adjoint has been implemented historically in several groundwater modeling codes. It was in GRASP, it was in MODFLOW P. There was a version of MODFLOW 2005 that some folks at INTERA added the adjoint to, among others. But the question is, why do we still not have an adjoint with our production level MODFLOW codes? And the problem is the adjoint is intrusive. And what I mean by that, the way we solve the adjoint equations, which we'll see in a little bit, depends very strongly on how the forward solution is implemented in the code. That means somebody has to go into the modeling code and change it. Historically, they have to change the code, and that leads to long-term maintenance and upkeep issues to support an adjoint. A little bit of terminology for adjoint people. So we don't talk about outputs, we don't talk about observations, we don't talk about forecasts, we talk about performance measures when we talk about the adjoint. So the performance measure is one or an aggregate of model outputs of interest. Those can be historical, so past groundwater heads, past groundwater fluxes. It can also be the objective function from calibration, so we can treat the objective function as a performance measure. They can also be the forecasts. The future fluxes from the system can be a performance measure. So that's just the word we use in the adjoint world to talk about the outputs of interest from the model. Parameters are still there. That's the other side of the adjoint equation. And so we talk about properties, K, storages, but we're not talking about zones or pilot points. We're talking about grid scale. We're talking about the hydraulic conductivity in every model cell as a unique parameter. The storage in every model cell is a unique parameter. Boundary conditions, pumping, recharge, conductance and stage for mixed type boundaries. We're talking about every boundary node, every stress period as a unique parameter. So very high dimensional on the parameter side, but as we'll see, there's no computational penalty for being this highly dimensional with parameters. Okay, I'm a little bit nervous about this part. I'm going to be honest. Mohammed is the brains of the outfit on the mathematics behind the adjoint. I stole some of his slides to use today, but I'm going to try to give you a flavor of what's going on with the maths because I think it helps build a conceptual understanding of what the adjoint does. So first, let's just look at the standard solution of equations that MODFLOW 6 solves. So we have a conductance matrix A times a head vector H equals a right-hand side B. And MODFLOW marches forward in time, each stress period, each time step, solving for that head vector. Now we'll notice that conductance matrix A, it's a function of a vector alpha and of the heads at the current time step. That's the nonlinearity in this solution process. That vector alpha, that contains all of our conductances, our boundary condition elements, our hydraulic conductivities, those are all stacked into that vector. And you'll also notice the right-hand side B also depends on alpha and the heads at the previous time step. So that's the standard way MODFLOW moves forward in time, solving for the head vector. What we care about, though, is our performance measure. So we're going to call performance measure J. It's a summation over all the simulation times from k equals 1 to n of some function f. And the f also depends on alpha in the heads. But what we really want to get to is what is the partial first derivative of J with respect to each element in that alpha vector, each hydraulic conductivity parameter, each storage parameter. What's the relationship between the performance measure and all those parameters that we're interested in? So once we've run MODFLOW once, we take that same conductance matrix A, we take the right-hand side B, and we take our performance measure function F, and we solve a new system of equations. This system of equations, though, we go backwards in time. So we start with the last stress period's conductance matrix, the last stress period head vector that MODFLOW solved for, and we solve for something new called lambda. Lambda is the adjoint state vector. So we march backwards in time, solving for those lambdas using the heads and the conductance matrix and the right-hand side from MODFLOW. You can see here in these equations, though, where that sort of intrusion into the forward solution process comes. We need exactly the same conductance matrix. We need exactly the same right-hand side and exactly the heads that MODFLOW was solving for to solve for this adjoint state. Once we have all those lambda vectors, then we can apply this equation to propagate those lambda vectors to the parameters we care about to get our partial first derivatives. So there's a direct effect with the partial of the performance measure with respect to each parameter. And there's also the indirect effect. Again, conductance matrix, right-hand side are featuring heavily in this equation as well. So again, there has to be a tight coupling between the forward solution and the adjoint solution. Okay, if you made it through that, awesome. Now we're just going to talk a little bit about conceptually what that adjoint state represents. The adjoint state, the numbers in that lambda vector, there's one number for every active model cell, and we solve for that vector for every stress period. And what that is, that number is the sensitivity of the performance measure to a unit injection of water in each model cell. So if we were going to do perturbation style, we would go through each model cell, inject a cubic meter of water, run the model, and see how the performance measure changed. And go to the next cell and next cell. Now, we don't have to do that. We don't have to do that. We just solve the system of equations, but that's what that number is in lambda. And that means just by getting that lambda vector, we have the sensitivity of the performance measure with respect to pumping and recharge, even if that model cell has no pumping or recharge. I'm gonna let y'all marinate on that for a minute while I get a drink, because that's a pretty powerful quantity. Okay, now we're gonna take a slight detour into the world of capture fraction mapping. Capture fraction mapping came from Stan Leek. It's a form of sensitivity analysis, and it's a response coefficient between groundwater pumping and simulated surface water groundwater exchange. We're focusing on this because a lot of applied groundwater modeling deals with this relationship between groundwater use and surface water. Because again, taking groundwater affects the surface water system. So what Stan figured out was he could go model cell by model cell, put in a new well, pump that well, and see how the simulated flux between surface water and groundwater changed. And so this quantity ranges from 0, which means that new well has no effect on surface water, to 1, which means it's a 1-to-1 correspondence between pumping and losses from the surface water system. So it's a pretty powerful quantity. The problem is, though, there's our loop of suffering again. We have to run the model so many times to do capture fraction mapping. If your model is slow, you're not going to do this until the very last part of the modeling analysis, which is unfortunate. But if we think back to our adjoint state, if the performance measure that we're interested in is the simulated surface water groundwater exchange flux, the adjoint state is the negative of the capture fraction, which means now we can do capture fraction mapping with one forward MODFLOW run and one adjoint solve, and that's it for the entire model domain for every active model cell. I find that a little bit mind-blowing myself. That's pretty amazing. I get questions a lot about how does the adjoint work in the pest world. Well, in the pest world, when we're dealing with finite difference derivatives, the number of parameters controls the computational demand because we have to run the model once for each parameter to get those finite difference derivatives. In the adjoint, it's the other side of the house. The number of performance measures controls the computational demand. One performance measure, one adjoint solve. 10 performance measures, 10 adjoint solves. I will note, though, there's only one forward MODFLOW solve required. It's just the adjoint solves that we have to repeat. So it's a little bit different than what we deal with in pest. Okay, we made it through the maths. Now for the fun part, the code design and implementation. So our design goals, well, we want to avoid the trap of the previous adjoint implementations where we can have a code that advances along with MODFLOW 6. MODFLOW 6 is quickly becoming industry standard. It's a framework type of code base. It's fresh. It's evolving quickly. New things are being added to it. We don't want to have a separate version of MODFLOW 6 that does the adjoint. We want it to be working with MODFLOW 6, but we don't want to get in the way of the MODFLOW 6 developers either. We want our code to work with almost any MODFLOW 6 GWF model. So that means we want to cover the Newton and the standard solutions. Those two solutions have very different approaches to how you solve the adjoint equations. And we want to work with structured and unstructured meshes. We want a wide range of performance measures and a wide range of parameters. Now, realizing those two things require new equations to be derived and new equations to be implemented to support. And we want it to be open source and free because it's 2026. The key to what we figured out with this lies in the MODFLOW 6 API. The MODFLOW 6 API lets us access those solution components without having to modify MODFLOW 6. We can get the conductance matrix, the heads, the right-hand side, a variety of other quantities without us having to change MODFLOW 6 at all. That's the key to this thing. That makes it non-intrusive-ish. On the code side, there's a MODFLOW 6 ADJ class. That class solves the forward model one time via the API, collects the solution components, conductance matrix, right-hand side, saturation, head vectors, stuffs all those into an HDF5 file, and that's it. This is where we dust our hands of MODFLOW 6 and put it away. And now for each performance measure, we make a performance measure class instance. That instance tells us the type of performance measure, head, flux, residual, other. It tells us where it occurs in space and time. And it may also have the observed values and weights if this is an objective function performance measure. This performance measure class loads up that HDF5 file that the other one wrote, that's the forward solution, solves that adjoint state system of equations, propagates it to all the different parameters, and then puts all that information into a new HDF5 file. Simple as. Currently, we have well flux, of course. We have recharge. We have horizontal and vertical conductivity. We have storage. And then we have a variety of boundary condition elements for the mixed type boundaries, including SFR. So we have SFR stage and conductance as parameters. So you can see how your performance measure is influenced by SFR stage and conductance. On the performance measure side, we have head, so we can do a single simulated groundwater level at a point in space and time. We can do a time series at a single point across multiple times. We can do a region of heads at a single time, or combinations of those, all mixed and matched however you want. Same thing for the flux between a groundwater node and a boundary condition. It can be a single point fluxed from one groundwater node to one boundary element. It can be a time series at that same one. It can be a combination, any way you want to slice it. And we also support the sum of square weighted residual. So the standard weighted L2 norm objective function that we're used to from pests can also be a performance measure, as long as that objective function is only in terms of heads. On the solution techniques, there's a direct solver to solve that system of equations to get those lambda vectors. But in most cases, when we're talking about real world scale, large groundwater models, you're going to need an iterative solver. And so Joe has hooked us up with a preconditioned biconjugate gradient stabilized solver, similar to what's in the IMS of MODFLOW 6. And there's a lot of new work going into exposing those solver options for users. Right now, the code is available under INTERA's GitHub organization as MF6ADJ. If you search for that, you'll find it. We're working on getting it deployed through PyPI, so you can just do pip install. That'll hopefully be ready in the next week or so. We also have a read the docs. Again, Joe is the master at this stuff. The example notebooks are now rendered on read the docs, so you can see how the example notebook should look for you if you run them locally for yourself. And there's an open access publication in groundwater if you want to learn a little bit more about it. Okay, example problems. How are we doing on time? Doing good, doing good. Okay, the first problem, this is a simple synthetic two-dimensional cross-section model called the Zidell problem. So it's an XZ cross-section. We introduce some water over on the left side at the top. It flows over each one of these stair steps and leaves the model down at the bottom. And it's a good stress test for the Newton solution, and also a good stress test for us on how we're implementing the companion adjoint solution to the Newton solution. So we're interested in the groundwater level at that red triangle. That's going to be our one performance measure. What is the head right there at that red triangle? So we implement our little piece of code. That's all you got to do. And we can make plots. This is the plot of the adjoint state vector. So where it's dark blue, no amount of pumping is going to influence the head. Where it's bright yellow, it's very sensitive to pumping. And so you get an idea that on the lower lobes, you can do whatever you want. You're not going to influence the head at that red triangle. Same thing on the top lobe. As you get closer to the left boundary condition, any sort of pumping there is going to be buffered by that GHB boundary condition and not affect the head. But then immediately upgrading of the head and on the lower above it, any amount of pumping takes water from the system that would have otherwise supported groundwater levels at that red triangle location. We can propagate that to hydraulic conductivity. This is not the pattern I was expecting to see. We verified it with perturbations. What you see is there's a lot of places where hydraulic conductivity does not affect that simulated groundwater level at that red triangle. On the top lobe, there's a positive relationship, because if we increase K there, more water flows in from the boundary condition, flows down, affects the groundwater level at the red triangle, and then immediately down gradient of the red triangle on the same lobe, if we turn K up, the water flows out faster, which then lowers the groundwater level. So there's a negative relationship. But everywhere that it's green, you can change hydraulic conductivity pretty much whatever you want, and it's not going to affect the groundwater level. Again, this is a little bit counterintuitive, but it helps build that hydrosense that I was talking about earlier with using sensitivity analysis earlier in the process to learn about your model. The San Pedro model, this is where Stan Leek actually first demonstrated capture fraction mapping. Joe converted it to MODFLOW 6 for us. It's a structured transient 10-year simulation. The focus is on simulating the relation between groundwater use and surface water groundwater exchange with the SFR network. So our one performance measure is going to be the simulated exchange between the MODFLOW 6 GWF model and all the SFR reaches as one number. To do this analysis, it's one MODFLOW 6 run, one adjoint solve. There are 115,000 active nodes, which means you would have to do heaps and heaps of model runs if you wanted to do this in the perturbation style. There's the code you have to run. It's the same code I showed before. And now we can make maps. This is the map of capture fraction. So the relationship between groundwater pumping and SFR exchange for layer 4. Where there's a yellow color, that means within that 10-year window, groundwater use at that location does not affect the simulated flux between the groundwater system and the SFR network. Where it gets closer to -1, especially when it's -1, -1 says groundwater pumping here, every unit of water I take out of that well is being taken directly from the SFR network within that 10-year simulation. Pretty powerful quantity. We can make other maps, no additional runs, same one MODFLOW run, same one adjoint solve. We can look at the same quantity in layer 2. Again, 0 to -1, same quantity in layer 5. No additional runs. This is all the same thing. We're just making plots. One model run. And we can also visualize some properties. This is where vertical hydraulic conductivity in layer 5 influences simulated surface water groundwater exchange. One model run. This is another example we've been working on. This is a patterned after a mine dewatering problem. The red square in the middle, that's the pit we're trying to dewater. Those red squares are groundwater pumping locations. The distributed little red dots on the left side, that's the reinjection locations. And on the far left, that far left is where we're concerned about surface water groundwater exchange. That's a river, and we want to protect that river, but we want to have the mine open for dewatering. So we have 3 stress periods: a pre-mining steady state, a 10-year transient active mining, and then a 100-year closure period. So we can run first the active mining surface water groundwater exchange performance measure using this piece of code, and we can make this map. This map is showing us where groundwater pumping or groundwater injection during active mining affects the flux to that river during active mining. So you can see the 0.2 runs right through the mine pit. That means 20% of the water that's being used for that's being extracted for dewatering would have otherwise made it to the surface water network. We can also see the reinjection wells. They're right around the 0.5, which means reinjecting water there, 50% of that water makes it to the surface water network by the end of the mining period. Pretty cool. We can also solve another set of equations. What's the relationship between pumping during mining to the flux at the end of closure? So what's the lag between dewatering during mining? How's that going to affect post-closure? Well, that's this map. This says if we want to really protect the surface water system during mining, we need to be injecting water right there inside of that 0.32 contour, because that's where we're going to get maximum benefit to the surface water network. So while we're mining, that's where we should be sticking water, because that's going to make most of it get, the 30% of it's going to make it to the surface water network by the time we're done mining. That's pretty cool. Pretty cool in one model run. Okay, I'm a little bit nervous to present this as well. My understanding of the utility of continental scale models for decision support seems to be pretty low at this point, but makes an awesome picture. So the USGS has a collection of MODFLOW 6 models that cover all of the US. Joe and I realized, well, why don't we just make a capture map for all of the US? And so these models were originally developed by Wes Zell and Ward Sanford. They're freely available. They're consistently developed and calibrated. So it's a nice way to get to use these things. Grab them off the internet, apply this tool. Same type of code. It's just now we're looping through and solving this equation for each one of those little sub-models that cover the continental US. And so there you go. That's a 5-year surface water flux performance measure. And that's the well capture fraction map, essentially. So where it's 0, we see very little capture from pumping within 5 years. Where it's bright yellow, a lot of capture for pumping within 5 years. Nice picture. Joe has also been doing some statistical analysis with this. So looking at the cumulative distribution function for the whole US, and then splitting it east of the Mississippi, west of the Mississippi, and then looking at the 5, 10, and 25-year capture fractions and trying to understand how that stuff kind of stacks up. Pretty rad. So some future directions related specifically to performance measures. We're working on a cell-by-cell flux performance measure. So something related to, say, what you could do with zone budget. So looking at the sensitivity of a zone budget analysis as a performance measure. Turns out there's a little bit of complicated math that go into that, but Mohammed has a prototype going already. I think we want to look at using SFR stream flow as a performance measure. So not the flux between groundwater and surface water, but the actual stream flow. I would like to see some mixed residual performance measures. So we could use not just heads as the objective function, but heads and fluxes in the objective function. And then I think long-term, we really want to get to a transport adjoint solution so that we can use concentration or mass as the performance measure, and we can propagate that through to see how K and recharge and storage affect those transport quantities. There's a few adjoint adjacent things that we're looking at. Quasi-Newton algorithms are a type of optimization tool or calibration tool. They don't need the full Jacobian. They just need the objective function gradient vector. Well, that's exactly what we get from the adjoint tool. So we can start to think about doing very large scale optimization efficiently with the adjoint paired with these quasi-Newton tools. There's also something called randomized maximum likelihood that comes from petroleum that uses this quasi-Newton algorithm to quantify uncertainty, similar to what you would get with ensemble smoother. There's another type of algorithm called Hamiltonian Monte Carlo that's more closely related to Markov chain Monte Carlo, but it works well in high dimensions, but it needs those gradients. So we're looking for implementing the adjoint to get us the likelihood function gradient or the objective function gradient within that sort of metropolis sampling algorithm. And then further down the road, I do think having that gradient information has got to make statistical model emulator training more efficient than what it is now. So we're starting to dabble in that a little bit as well. Okay, that's about it. I want to say thank you very much to the INTERA leadership team for providing financial support for Mohammed, Joe, myself, and Katie to work on this tool. Eternally grateful for that. And thanks again, everyone, for attending. And we'll jump on some questions if you have any more in the chat. And maybe Mohammed and Joe might pop in, go live on camera. All right, I think we got Joe. Okay, let's see. I think Joe and Mohammed picked up a lot of questions during the presentation. Michael's asking, are there any packages that are not supported with the adjoint method? I'm not sure if Lake is supported yet. I don't think C-sub is supported yet. Maybe Mover. Joe, do you have any of those comments about which packages may or may not be supported so far?
I guess, they'll work with all of these things as far as I know, like Mover, but I'm not sure that, we don't have any performance measures or anything like that for those.
Right.
I'm not 100% sure, but I think generally you can run a model with all of these things. I think it just becomes a matter of whether, there are no sensitivities necessarily going to be developed for them or any way to kind of evaluate them relative to a particular performance measure at this point. I think the only one that I've run into
I guess just
created a problem was, I think, ghost nodes. That's the only one there was a bit of
ghost
weirdness.
nodes.
Yeah.
Right. Yeah. So some of those advanced packages and then the ghost node correction might be a problem at this point. But again, I mean, we're actively working on this, so we're hoping to build it out to be a more full feature as time goes along. David was asking, what is the computed adjoint sensitivity for hydraulic conductivity? It's the partial first derivative of the performance measure with respect to hydraulic conductivity directly.
So there is no specific time for each parameter. The main time is when solving the adjoint system. So the time required to calculate the sensitivity for each parameter, it's just applying these formulas. So the main time is solving the adjoint system.
There are some example codes on GitHub already in the example folders in the repo. So there's the San Pedro model is there. The Zidell problem is there. I think, and there's also a few others. So there are examples on GitHub. I should have mentioned that if you want to check out some example notebooks. So David is asking, can we set a performance measure for drawdown? I think that's the same performance measure as if it was head in terms of sensitivity.
Yeah.
Is that right?
Yeah, that's correct.
Awesome. All right, I'm not seeing any more questions pop up. Oh wait, we got some. Here we go. How are the head observations passed in? So when you define the performance measures, we have information about what cell it's in, what simulation time it corresponds to, and then for those residual based performance measures, you actually put the observed value and the weight on that same line when you're defining the performance measure information, and then it can propagate that to that objective function performance measure. Chris is asking, can we clarify when this code runs? It is not concurrent. We have to run all the way to the end so that we can get all those components, and then we go backwards in time. So we run MODFLOW 6 once, and then we go backwards in time to solve for the adjoint. Yes, MODFLOW 6 and the adjoint are set up to run for unstructured and structured grids. But like Joe mentioned, there might be a little bit of an issue with the ghost node correction with the adjoint solver at this point.
And I guess I don't remember if you said this. It currently is only limited to running a single model. So like if you had a multi-model simulation, it's not set up to run. It probably will run on the first one. I don't remember if we error if it's a model with more than one model in it, or a simulation with
Right.
more than one model.
Yep. Thank you, Joe. Someone is asking, there seems to be no reason not to use the adjoint state in parallel with PEST if an adjoint solution exists. That's true, but again, like the PEST framework we deal with where we're trying to fill a Jacobian is not set up to deal with really massive numbers of parameters. So when you get into like 100,000 parameters, that Jacobian is going to become too large to handle just for the PEST algorithm itself. Mohammed, do you want to take that question from James? Do you see that one?
James.
Yeah, he's asking, are the performance measures time invariant? Other time variant stresses don't affect the performance measure through time.
No, they could be time variant. Time invariant. No, the performance measure could be any combination of heads at any times. So it's not necessarily time invariant.
That's an interesting question about running the adjoint in parallel if you have a large number of performance measures. I think Joe and I've actually talked about doing that. I think you could run it in parallel if you have lots of performance measures. Let's see. Do you guys want to take any of the other questions?
I guess I don't think you get the coefficient matrix at convergence, and that's essentially what it's doing. It's basically the converged coefficient matrix is what's being used by the adjoint during the solve.
That's right.
And there was a question earlier, I don't think there was talking about nonlinear effects. And I guess one of these assumptions with the adjoint is that, again, that it's a linear problem that we can deal with, right? That coefficient matrix, right? That when we do the adjoint back in time, we're assuming that it's linear. The problem is linear.
That's right. We're also assuming that the relationship, I mean, it's a point linear approximation to the gradient, so that the value of hydraulic conductivity and storage and other things in the model, we're calculating the sensitivity at that point. So if you change conductivity and storage and other things, you might get a different sensitivity depending on those values. But again, you can quickly calculate those sensitivities and estimate those sensitivities across a range of conditions if you wanted to. Hey, Mohammed, can you take this question about comparing the sensitivities for different parameters between K and recharging or ribbon conductance? Are they somehow scale dependent, or are they directly comparable?
I mean, they have different units, so they are not directly comparable, but we can normalize them. So normalize them to values between 0 and 1, and then
there you go. So Luis is asking, have we tested this on big models, and what's the performance using standard methods like IES or PEST? We're not quite there yet. I mean, that's what we're working on with that quasi-Newton tool, because that quasi-Newton tool can use the adjoint gradient vector, but we don't have a direct comparison with what PEST HP and IES are doing yet. I don't think we support the UZF yet in terms of propagating UZF parameters to the performance measures. It's something we could look at, though. Let's see. Jack is asking, if the observation is transient, do you need more runs to understand the sensitivity between the observation at a single time? So that depends on your performance measure definition. You can get the sensitivity to the whole time series as one run, but if you're looking at specific times, that's a specific performance measure. So you need to solve the adjoint system of equations once for each one of those performance measures. So maybe you want to look at low flows every season. So like you could group all the low flow times together to be one performance measure. But if you want to look at each season, that would be a unique performance measure to solve. Let's see. It's not possible to use this with MODFLOW own. This is like specifically tied to MODFLOW 6 because, again, the adjoint depends strongly on how the forward system of equations is solved, and we need the API to access those solution components. So this is a MODFLOW 6 only compatible tool at this point. To install to get MODFLOW 6 ADJ, there are instructions on the GitHub repo, and we're working to get it on PyPI pretty quickly so that you could do pip install MF6 ADJ. So there's not a tool in the pest world yet that uses these types of it, that uses the adjoint gradient vector yet. There's a guy named Reiji, and he's working on a tool that will be able to use that, implements that quasi-Newton solution technique. And so we're hoping with that, we can just read the sensitivity vector in directly from the forward run to use it for history matching and or constraint optimization kinds of things. So we're working on it on the pest integration side of things. All right. I think that's about it. Joe, Mohammed, any final thoughts or questions?
None for me.
Okay. Oh, Joe, someone's asking about how the head closure affects the adjoint sensitivities. I think you've done into that a little bit. Yeah.
Yeah, I mean, it would have to be small enough that, again, this unit injection, that you can see it and that you get a meaningful sensitivity. So there might be some cases where if you had too loose of a head convergence criteria, that maybe you wouldn't get very good sensitivities out of that. I don't know if Mohammed, you have any thoughts on that?
Sorry, I didn't. I wasn't in the question. What was?
It was just
we were just discussing, like, sorry, go ahead, Joe.
The head convergence criteria. If that's too small, right? That unit injection of water that we essentially apply in the adjoint, it may be that your head convergence criteria doesn't give being too loose would give you poor sensitivities potentially.
Yeah, sure. The sensitivity calculation should also depend on the head. If the head is not so precise, so this will affect the sensitivity, but this is not related to the adjoint method itself. It could happen for the perturbation method also. So yeah.
That's right. Yeah, it's not characteristic of the adjoint. It would just be characteristic of sensitivity analysis.
Yeah.
Iman's asking, is it true that the adjoint computational cost for one performance metric is the same as one forward run? I think that's more or less true. Like solving the adjoint system of equations is just about as expensive as solving the forward system of equations. Does that sound right?
It's mainly because of this memory, storing these heads and so on. But the solving the adjoint system itself, it's even less because it's linear. It's always linear. So we don't need to do these iterations.
Yeah, that's been my experience. Like, unless it's a confined problem, again, the adjoint usually takes fewer iterations to solve than the similar time step for the forward run.
All right. Well, I guess we'll wrap up there. Thanks everyone for attending. There will be the recording posted pretty soon. And if you want to try MODFLOW 6 ADJ, it's on GitHub. We monitor the GitHub repo for discussions and issues. If you have questions or you have a comment, we will also respond there. But thanks everyone for attending, and we'll see y'all next time.
Thank you.